So welcome to the first afternoon session of this training school, and we continue the series of interesting talks with another interesting one given by Erez Nesharim from Technion, and he will speak about Schmidt games and applications in dynamics and number theory. Erez, the stage is yours. Erez? Okay. Erez, I just introduced you, so you can start your talk if you mind.
Okay, thank you. Let me just, something just happened. I was kicked off.
Not by me for sure.
No, it was related to the recording somehow.
We see you.
Okay, so you see me and you hear me?
Yeah.
So thank you very much for inviting me, and thank you very much for organizing this training school, and thank you very much for coming to the talk. I'm going to repeat what Arkady said about how pleasure it is for me to be here, and how I'm honored to speak here. So I'm going to talk about Schmidt games. Maybe the talk will have a slightly different flavor from the previous talks, but definitely related. I enjoyed very much the previous talks, and looking forward for tomorrow and the day after. And I will also try to be playful in my talk, so you can feel free to interrupt me whenever you want. So the interest in applications of game theory to number theory and dynamics started with Schmidt, Wolfgang Schmidt, and he realized that some natural sets that are studied in number theory and dynamics are best described using games. Then he had many interesting questions and some of them, in some cases, the breakthroughs towards interesting questions in number theory and dynamics came from better understanding of the game theory that is involved. So it's very probable, it's very likely, it could be that also the next breakthrough will come from a better understanding of the game theory that is involved. And this is why I'm very happy to speak in this conference, and very happy to see that people in game theory are interested in applications. So the interest is mutual. Okay, so I'll talk about Schmidt's game, the original game, and then about maybe a slightly more suitable version, and then I will invest most of my time in two applications in dynamics and number theory, and later I will talk about two classical applications, and then later I will talk about a more advanced or more recent game, and maybe just mention generalizations of those applications. So Schmidt's game is played on a complete metric space. It's common to call the players in this field from some time on. It became common to call them Alice and Bob, and they have each of them have a parameter, alpha and beta, and the alpha beta game is played is an alternating move game. Where Bob starts and he picks a starting ball, and then Alice chooses a ball inside that ball, and the radius of that ball should be alpha times the radius of the previous of Bob's ball, and then Bob chooses a ball inside Alice's ball whose radius is beta times the radius of the ball of Alice. And then in the end there is an outcome. So the intersection of all those balls, since this is a complete metric space, there is a point, and that is the outcome. So let me draw this in a picture. So this is the first time I'm giving a talk, this kind of a hybrid talk.
Can you bring the previous slide just to remember the?
Maybe, yeah. I'm just going to draw the picture now, okay. So it will become what?
I see. Okay, I wanted to notice the difference in the power bit, the different roles that alpha and beta are playing. Yes. Okay.
Yes. So there is B0, and then so this is the first time I'm giving this kind of a hybrid talk. So hopefully it will not be very bad. So this is A1, and the radius of A1 is alpha times R0. The radius of B0 is R0, and then inside A1, Bob has to choose a ball of radius beta times alpha times R0. This would be B1, and the game goes on. So in the end there is in the end there is a point, and that is the outcome. So this falls into the category of games, as Arkady mentioned in his talk. Those topological games, or more specifically, those games played on a metric space, they fall into the category of games that are studied in Martin's theorem. Okay, so one thing to notice. Okay, so now a set is called winning. So a subset of the space is called winning if there are. It's called alpha beta winning if Alice has a strategy which makes sure that the outcome is in S. So those type of winning sets, they are not very nice if you fix alpha and beta. It's easy to see that they are dense. If S is winning, if S is alpha beta winning, then obviously it is dense, because no matter Bob can choose his first ball arbitrarily. So, and if Alice can make sure that some point in this ball is in the set S, then S must be dense because it has a point in every ball. But for example, Chris Freiling gave an interesting example of a set that is 1/2 winning, but not 1/3 1/2 winning. So this is a bit misleading, because you may think that being winning with a smaller parameter is harder, because Alice, in order to make sure that the outcome is in her set, she must shrink towards that point in a faster. So if alpha is smaller, then she can do it faster, and then maybe it means that being alpha beta winning with smaller alpha is stronger than being alpha with a larger parameter. But this is a bit misleading. But anyway, we'll not touch this, because we'll have this better behaved alpha winning property, where Bob is actually allowed.
May I ask a question at this point?
Yes. Sure.
So alpha, is it so does Alice have to choose exactly the ball of exactly radius alpha times the ball of Bob, or is alpha an upper bound on the radius?
No, if alpha is an upper bound, then this is not interesting. I mean, this will give too much power. This will be like the Banach-Mazur game. So here you want to restrict. There are versions of this game where Alice can actually choose a slightly bigger ball, like alpha would be a lower bound on the ratio. And those type of games, they behave a bit better, but it's even harder to prove things about them. And I don't want to get into all the versions of Schmidt games. There are many. So unfortunately, I will not be able to touch. Elon asked me to touch the dimension game, but I will not be able to. I will not talk about that. But that could be for later maybe. More questions? Okay, so a set is alpha winning if Bob can, if no matter what beta is, it is alpha beta winning. So in other words, you can think of it as allowing Bob to make in his first move of the game. He can also choose beta.
He can choose beta once and for all.
He can choose beta once and for all. Yeah, okay. In the first move of the game.
Yeah.
And since we are interested in the well, coming days, we are going to be interested in games with values, then I can say that you can define the winning dimension. This is defined by Schmidt of S to be the supremum over all alpha, such that S is alpha winning. And then you can even allow Alice in the first move of the game to choose alpha, and then she will have to choose alpha wisely, not to choose it too large, because then it might be not winning, and then there will be some supremum. So actually, it's an interesting it's an interesting question that was not in the attention for some time, or maybe it was known as a folklore that the supremum is actually achieved. So in the literature, there are many sets that are proved to be alpha winning for every alpha that is smaller than 1/2, because this is easier to work with alpha that is strictly smaller than 1/2. Because if you allow in the case alpha equals 1/2, you must if there is a ball and Alice has to choose a ball that is exactly 1/2 in the radius, then it must contain the center of the previous ball. So this way, it's a bit annoying to work with. So people usually prove that sets are alpha winning for every alpha that is smaller than 1/2, but then there is a general result that tells you, well, not a general result, but there is a result that tells you that actually you can also win with 1/2. I don't know if this follows from any abstract game theory result.
So, Erez, is it clear that for every set S there is an alpha for which the set is alpha winning?
I guess if alpha is 0, then Alice can just write, alpha is not 0. Maybe we can allow alpha to be 0 then, and then if alpha is 0, then just choose the center. But no, I don't think so. If you not allow alpha equals 0, then most sets are not winning.
Mm-hmm. Okay, thanks.
So this is the main property that led actually to Schmidt's interest in game theory, is that if there are countably many alpha winning sets, then the intersection is also alpha winning. Since alpha winning sets are dense, this would mean that that at least in particular it's not empty. So if you want to prove that something, that some number, for example, have infinitely many, countably many properties, then you might as well prove that the property is winning. Obviously, you may think of other ways to do that, like category and measure, like proving that the set has full measure, then the intersection also has a full measure. But in this case, the sets that he was interested in, they were actually small in the other sense. So they had 0 Lebesgue measure, for example, and they were first category. So, but they are still large sets. And the proof is very insightful. You just play the game, like you just play a simultaneous game using the winning strategies of Alice for each and every set. So the picture to think of is that you fix some winning strategies for Alice for each of the sets, and then on the first move you play according to the winning strategy of Alice for S1, and then on the second move you play the winning strategy for S2, and the third move you play again the winning strategy for S1, and you do this nice shuffle. So you make sure that you play every strategy infinitely often. So here the distance between the appearance of ones is 2, and the distance between appearance of twos is 4, and the distance between appearance of 3 is 8, and so on. And maybe there are more things to say here, but since we are dealing with alpha winning sets, then it means that you are alpha beta winning for every beta. So you might as well think of, well, the jump from here to here, the jump from here to here, for example, the balls shrink by alpha to the alpha to the 8, beta to the 8. So you might, okay, you may think of this as being Bob's ball in the alpha alpha to the 7th, beta to the 8th game, and then Alice would just have to make her move, this move, and then this would fit. So it doesn't matter what happened between the two appearances of 3. Okay, maybe this is standard thing in game theory. Let me know if I'm elaborating too much, or if this is. Elon, you don't look happy. Yeah.
I don't follow the proof. I do not know whether the others do, but for me, somehow the fact that you apply the winning strategy of S3 every 8 times, where alpha was shrunk by alpha to the power 7 or 8, it doesn't really matter, but not with the alpha. So I don't see.
Yeah, the alpha remains. The alpha stays. So I only know how to.
Okay, so you add it to the beta.
Beta prime is. So I'm using the alpha beta prime.
Okay.
Strategy.
Yeah. Okay. Then at least for me it's fine now, but I do not know about the others.
Erez, are you forgetting a part of the history here? I'm not sure how you are forgetting it. Could you maybe just say 1 or 2 words more?
Yes. Thank you, Arkady. I'm forgetting because there is a general phenomena that there are always, if there is a winning strategy, then it's local. So you can actually forget about the history. I don't know if this is a general fact about topological games or in a more restricted category of games, but you can also do everything without this result. So you can also remember all the history, but here it's just more convenient to work with the local version. But what I'm not forgetting is the B0. So the B0, for example, prime here is really the B 0, 1, 2, 3. So really it is the B3 of the original game. So this I'm not forgetting. Just in the notation, I'm not showing this.
So it might be that this winning strategy is subgame perfect, and therefore it is winning in every position. So all you need to know is the current position, which is the current set that you are in.
Yes, that's how it's called. You're right. It's called positional strategy. I'm not completely sure how to prove this or why this is true, but this is a general fact, which is very useful, and was proved by Schmidt in his 65 paper. Okay, so the next thing I want to do is I want to show you an example of a winning set and how it is useful. But in order to do this, it is more convenient to work with a more evolved or more recent game that was invented by McMullen in 2009, I guess. And that's the absolute game. And the difference is that he called it absolute because it doesn't involve the alpha. It only has one parameter, beta. So basically, now Alice and Bob, they still choose balls, but the rate in which the balls decrease is the same. And the difference is that, now Bob has to choose a ball that doesn't intersect, that is away from Alice's ball. So if you don't need this, but if I draw this, then this is B0, this is A1 of radius beta times R0, and then this is B1, and the game goes on inside B1. So this is A2, and this is B2, and so on. And the game still ends in a point. The game still ends in a point. And this will be the outcome, and everything is basically the same. You can define the set. Well, here McMullen worked in Rn, but really you can define this for every metric space, every complete metric space with one cost that absolute winning sets will not necessarily be large if the space is small. But so you need the space to have enough points in order for absolute winning sets to be large. But you can still define. You can define the notion over every complete metric space. Yeah.
What is the motivation to call it absolute winning?
Absolute, yeah, I just said it that.
Okay, sorry, I was thinking at the same time of what was on the slide, so probably I missed it. Sorry, Dan, you don't have to repeat it.
Okay,
I'm listening and thinking simultaneously. So, okay, sorry.
No, but really, I really appreciate every question because it allows me to talk more. So about the point. So really, there is one very useful property of winning sets is that if S is if S is alpha winning, sorry about this. If S is alpha winning, then you can apply an F is some B-Lipschitz function. B-Lipschitz. Oh no. Sorry if I mess this out. Then f of S or f of S is alpha prime basically, I think it should be divided by this, well, Lipschitz constant square, alpha divided by the Lipschitz constant winning. So this is a bit frustrating because it doesn't allow you to use the countable intersection property for infinitely many images of an alpha winning set, because if the parameter shrinks, it is true that if this is smaller than alpha, then if this is smaller than alpha, then an alpha winning set is also alpha over m squared set, m squared winning. So you can have the finite intersection property, but if you have infinitely many images, then you cannot have the countable intersection property. And in the absolute game, there is no alpha, so you can in fact get the stronger result that absolute winning sets are preserved by B-Lipschitz functions. So it's just a nicer game, but I don't know if this is the best name. It has some reason. He had some reason to call it this way. Okay, so here there is another subtlety that that wins by default. So if the space is not large enough, it might be the case that there is a ball in which all the set is concentrated in a smaller ball, and then Alice can choose this set, and the game will end because Bob will not be able to choose a point from the space. But then this is not interesting. So in this version of the definition, which is slightly different from what McMullen used, we allow this, and we just we pay the price of absolute winning sets might not be large. So if the space is small and Alice can just win by default all the time, then being absolute winning is not such a it can be in empty sets even. So it's only true. Okay, here it is. So it's only true. So this is the definition of what I mean by the space being large. So a subset of a metric space is called diffuse. If there is some radius and a parameter beta such that, okay, let me draw this, such that whenever you have a ball around X, no matter what other point Y you take, let's say this is Y, it can even be not in K. So no matter what other point, there will always be a point Z. So this is X. There will always be a point Z in the space in K, such that the ball around the smaller ball around the Z is inside the bigger ball around X, but do not intersect the smaller ball around Y. So this is what this definition is really adjusted to the game, but really it's a general it's equivalent with some difference in the parameters to being what is called uniformly perfect. So it's a kind of a uniform definition on being perfect, on having another point from the set in the near any point in the set. And now it's not difficult to see that absolute winning in diffuse sets imply winning. So we do not lose anything if we work with the absolute game. On the contrary, we also gain something. So one of the motivations was exactly this. maybe I can give you, I can give you the example you should have in mind for a diffuse set is the Cantor set. So is the middle thirds Cantor set. So you see that in every ball, so if the ball was on the level, on the scale of some level n of the construction, and beta, for example, was 1/3, then you see that there is some separation. So it's not true that everything that is contained in this interval is already contained in a smaller interval. So this is the example you should have in mind. And one of the motivation was to understand the intersection. For introducing the absolute game was to understand the intersection of those natural sets that appear in number theory in dynamics with the Cantor set, for example. So this is an ongoing research in number theory in dynamics to understand this for natural fractals. And here there is actually, so here also you see the connection to this conference maybe, or this summer school, where you actually also get the converse. So there is a nice characterization. What is not true about like alpha winning sets, where there is no other characterization that I'm aware of alpha winning sets. Here there is an actual characterization of absolute winning sets. So those are at least for Borel sets. So at least if the game is determined on S, really it doesn't matter that it is Borel. It matters that the game is determined on S. Then this characterizes the property of being absolute winning. So I don't know, should I prove this? This is somewhat in the spirit of the training school, and one direction is very easy. Let me try this. So one direction where you try to prove that, so if S is absolute winning, assume S is absolute winning, and K in X is diffuse and non-empty and closed. Then, since it's non-empty, there is a point. So let there exists some x0 in K, and Alice. Well, the set is absolute winning. So no matter what Bob is doing, we can make sure that Alice can win. So, for example, let's say Bob chooses B0 to be the ball around X0 with some radius. Let's say this radius comes from being diffuse, right? So if the set is diffuse, then there is some radius from that radius and on, whenever you have a big ball, it's not concentrated on small balls. So let's say this was Bob choice, and then, well, what we are trying to prove is that we're trying to prove that S intersects. We're trying to prove that S intersects K, right? So just play according to Alice's winning strategy, and make sure that also you get a sequence of balls which are centered in K. But this is exactly what you can do. So let's say A1 is Alice's choice, Alice's move. So this is a local we can think of it as a local game or a positional game. So Alice sees B0. The strategy tells her next move is A1. So Alice's move according to a fixed winning strategy, which we fixed in the beginning. So then there is so since K is diffuse, there exists, K is diffuse, there exists some Z in K such that this ball around Z of radius beta times R0 is contained in the ball around X0 minus this A1. So let this be B1. So and let this be X, well, no matter what it is. Bob's next ball. So you see that if you continue in this way, you get a sequence of balls that are centered in the fractal, but are also played according to a fixed winning strategy of Alice. So they must, the intersection must be in K because it's closed, and it must be in S because it's the outcome of the game that is played according to Alice's strategy. So this is one direction. The second direction, I'm not sure if this is very interesting. Maybe you can go back to this in the end if we have time. What do you think?
Erez, you mentioned that there's a connection to being uniformly perfect. So is one stronger than the other? Thanks.
I think they are. I think they are equivalent, but just there is slightly different parameter that you're using. I mean, you can either want a whole ball to be disjoint, or maybe you want just another point outside the ball. So this is the type of difference between the definition. Okay, so now I'm ready to give you the first application, or the first natural example of what. How am I on time? So the natural example is the set of badly approximable numbers. So maybe some of you feel comfortable with this definition, that these are all the real numbers that are far away from rationals. How far? They are far. They are so in Dirichlet theorem there are infinitely many approximations that are better than the denominator squared. And here, I'm just asking that up to a constant, it's the best you get. So that's equivalent to being a bounded type number. So if you look at the continued fraction expansion of X, then you just want the digits to be bounded. And here I just put this nice picture of rational numbers in the unit interval with all the rationals of denominators smaller than 20. So you see that some rationals they push away other rationals, like the rational 0. There are no, the closest to it is I guess is 1/20. Where other rationals, they may be, if the rationals have small denominator, they push away other rationals further. But it's not a uniform thing. And then the set of badly approximable numbers is somehow concentrated in the white areas, in the areas where, in order to see more rationals, of course there are more rationals because it's dense, but if you want to see them, you have to look farther, and then you have to increase the denominator, and then you may still get, since the approximation here depends on the denominator, you may still get points that are far away from every rational. Okay, so what am I doing now? So this is a small set. So almost every number is not badly approximable, but it is an absolute winning set. So let me try to sketch the proof for this. Okay, so let beta be some number, and B0 be Bob's first move. So I'm going to show to you that there is a strategy for Alice to make sure that she's far away from rationals, and she's going to have to choose some C. So fix some C that depends on beta and R0. We'll see exactly how it depends later. And then what Alice will try to do is she's going to try to stay away from rationals with the denominators that are between some two powers that are in certain range in every step of the game. So she's going to do it one step by one step, and then let's say, and I guess also choose some range, choose some Q. This will be the range, and then try assume that Bn do not intersect the balls around the rationals is empty for every P over Q with Q that is smaller than Q to the N. So here is my claim. In the next step, I'm going to want to deal with all the rationals that are between Q to the N and Q to the N plus 1. And the claim is that there is just one of those. So if I chose C and Q correctly, then there is just 1 point. So if there exists at most 1 P over Q with Q between in the next range between Q to the N and Q to the N plus 1, such that the ball around P over Q of radius C over Q squared intersects Bn. So, and the proof is very easy of this claim. And you just notice that if P over Q, if let's say P over Q, C over Q squared, and P prime over Q prime, C over Q squared, Q prime squared, intersect Pn, then the distance between P over Q and Q and P prime over Q prime, well, let's say P over Q Sorry about this. Let's say if P over Q is different than P prime over Q prime, then the distance between them, on one hand, it's bounded below by 1 over the denominator, the common denominator, which is bounded below since and Q prime and Q are between Q to the N, Q to the N plus 1. So 1 over, so it's bounded by below by 1 over Q to the 2N plus 1, 2N plus 2. On the other hand, since using just the triangle inequality, and well, and this picture, so if you have let's say this is Bn, and this is the ball around P over Q, and this is the ball around P prime over Q, then the distance between those centers is at most twice the radius of Bn plus the radius of the radiuses of the balls. So this is at most C over Q squared plus C over Q prime squared plus beta n plus, sorry, beta to the n R0. So now if we first of all, yeah, okay, wait. So the next thing will be, so this is smaller than 2 times C over Q to the 2n plus beta to the n R0. So if we choose Q to be beta to the, yeah, if we choose beta to be Q to the minus 2, so choose B to be Q to be beta to the minus half, then this is just this equals to, well, 2 times, right? 2 times the radius of the ball. So this is beta to the, well, two times C plus R0 Q to the minus 2n. And then if this constant was, so we got, in the end, we got 2 times C plus R0 Q to the minus 2n is bigger than Q to the minus 2n plus 2. So if this constant was smaller than Q squared, then this is impossible. And it's not a problem to make sure that those constants are, yeah, this is beta to the n, and this is beta to the n plus 1. So after beta is chosen, we can still choose the constant C to be, let's say, smaller than beta over 4, and R0 is never a problem, because we can just assume without loss of generality that R0 is whatever is small, because we can just play as Alice. We could just play the game until R0 becomes small and do nothing, just choose randomly. So we can assume that R0 without loss of generality, R0 is smaller than let's say beta over 4, and then we can choose C to be smaller than or even smaller than beta over 4 as well, and then this would mean this is impossible. Okay, so in the end, there is just one dangerous rational point in Bn, and this is going to be the rational point that Alice will choose in order to win the absolute game. So remember that she has to choose a ball of radius beta to the n plus 1 R0. So we just need to make sure that beta to the n plus 1 R0 is bigger than this constant over Q squared for this rational, so for Q that is in this range. But this is easy because this is possible. So just to make sure that this constant is small enough. Okay. I hope this was not too much. This took just 10 minutes, so I'm not very concerned about your attention. But now I'm going to. So, are there any questions about this proof?
Could you go back? Could you go back to the previous slide? Yeah, thanks.
I had in mind to give you another proof of another set being absolute winning, but I'm going to skip that. So I'm just going to mention it, but without giving you the full details. Okay, but this is great because we get for free that, for example, there is a badly approximable number in the Cantor set, which is natural to expect, but it's not so obvious to. Either you have a nice construction of such a number, or it's not a trivial fact. And also, what we get is this corollary, which was one of the motivations to introduce all this game theory, using this invariance under Bi-Lipschitz maps, or even differentiable maps. You get that there is some number that it and all its powers are badly approximable. Well, maybe this is trivial, but there is some non-algebraic number so that satisfies this. And this is non-trivial. So there are some algebraic numbers, quadratic irrationals that satisfy this, that are easy to show that they satisfy this, but there is an absolute winning set. So algebraic numbers are countable. So there is so this is another nice result. And I promised you also applications in dynamics. So here is a very natural subset of a very natural dynamical system that is absolute winning. So it's very, to me, it is very surprising that only now, very recently, we have the right language to describe the largeness of this type of set. So think of the times 2 map module 1. So you just take a number, multiply it by 2, and then take module 1, and so on. You get a sequence of numbers in the unity interval, let's say, and then you're asking, are there numbers whose orbits do not come to a neighborhood of zero, some neighborhood of zero? And obviously, it's not a common property. So almost every number will have a dense orbit under the times 2 map, but there are orbits that do not satisfy, that do not come close to zero, and this set is absolute winning. And I'm not going to show you the proof unless you really insist. Really, the proof is very similar. You show that in every range of multiplication of 2 to the n, there is at most one dangerous problem that can appear, and then this is going to be what Alice said. Right, those intervals that you're going to want to be away from. You want to be away from those type of rationals, like balls of this form for some constant c, and you show that there in every range, in every scale, there is just one problem. And then you get this nice corollary that there are orbits that if you choose randomly countably many points in the unit interval, let's say even a dense set, then there are orbits that what do I think? Yeah, because the constant may change, but so for every point in K, there will be a constant such that you stay far away from that point. There will be a CK that you stay away from that. Obviously, you cannot stay away from every point, from a neighborhood of K if K was dense. But if the constant depends on the point, then you can stay away from every point in K. Okay, hopefully I didn't confuse you. So let me know if there are any questions now before I go to describe another game. Also, another option is to take a 10 minutes break and then come back for another 15 minutes.
Well, I have a question. Okay, so if K is the set of rationals, how can you stay away?
Yeah, this is what I was confused about, but I was puzzled about. But for every point in the rationals, you stay away from the point in the rationals with a different constant.
Okay, so
this is a nice exercise in topology, right? To see that there is an open set that contains the rationals, but is not everything.
Okay, so the set on the left is closure of 2n to the power n times x. This cannot have a non-empty interior, right? Obviously, otherwise.
Wait.
The interior of the set on the left, the 2
I think
power
it can,
n times x must have empty interior.
Yeah. Exactly. That's the situation I'm talking about. It can have a non-empty interior.
Yeah. Okay. Wow.
It can have an empty interior. So.
Okay.
I mean, obviously, right? You can describe this set very easily if you have the base 2 expansion of X, right? So, for example,
yes,
it's staying away from 0 is just very similar to not having boundedly many consecutive zeros in the
That's
expansion.
true. Yeah. Yes.
up to being close to 0 from the other side. It's the same.
Yes. Okay, cool. Yeah. Okay, now I understand a bit better. Okay, thanks.
Sure. Okay, so the chance to get away with a break, you didn't take it, but maybe I'll still finish in 15 minutes. But this part is important to Elon because he was a bit worried that I'm going to only talk about games with winning or losing and not mentioning any values. So here's a way to get a value also in the absolute game. So now we have, this is like a way to quantify the absolute game with another parameter, alpha. But here the parameter is not used to facilitate the shrinking, the rate of the shrinking, but it's used to, where it is, to say how many balls Alice is allowed to remove. So if alpha is 0, this is just the absolute game. She's allowed to remove just 1 ball. But here, she's allowed to remove beta to the minus alpha. So again, we have this problem if the space is not large enough and there are no beta to the alpha balls in a big ball, then it's not an interesting property, but otherwise it's very interesting. It's not so trivial to show that's an exercise. I don't know how to do this. I have a way to see this, but the exercise is to show the countable intersection property for such intersection. Maybe this follows from some general principles in game theory, but it's not so easy to do this by hand. Okay, so what is the definition? So yeah, so again, the set is winning if Alice can make sure that the game ends in, is alpha counter winning if Alice can make sure that the game ends in S, or she wins by default. And then it's not so easy to show that it's absolute. It has the countable intersection property. So if alpha is 0, then this is easy because then the same proof works. But if the same proof that we used for Schmidt's game. But if alpha is not 0, then Alice would have to erase in the first. She would have to raise more and more balls, like a multiple of beta to the minus alpha. So it's not clear anymore that she can do with beta to the minus alpha, but she can. So this is not trivial. And again, there is a nice characterization of those counter winning sets for Borel sets at least. So this definition doesn't appear anywhere but in the literature, but I think it's natural to define a generalization of what it means to be diffuse. So now you have this alpha diffuse, and the difference is that you can erase the ball. It's not possible to cover big balls with beta to the minus alpha small balls. You need more than beta to the minus alpha balls. If you just use beta to the minus alpha, then there is another ball. So this is again this fits like a glove to the definition of the game. So if a set is winning on a alpha, if a set is alpha winning on an alpha diffuse space, then it's large. Then it's at least not empty, but it is large. And there is a characterization of alpha counter winning sets using this intersection property with the alpha prime diffuse subsets for every alpha prime. So this part is very easy. It's like the same. If the set is alpha counterwinning, then it intersects every alpha prime diffuse set with alpha prime bigger than alpha, and the converse follows from the determinacy of the game on Borel sets. So if you intersect every fractal K which is diffuse, alpha prime diffused for some alpha prime bigger than some alpha, then you are counterwinning. And let me finish with these two generalizations of the classical applications that we saw earlier. So you can try to approximate real numbers by algebraic numbers of degree D, and then if D is 1, then this is just the height is just very close to being the denominator of the rational, and then the algebraic numbers of degree 1 are rational. So you're away from rationals up to a constant over the denominator squared. And if D is bigger than 1, then you get another interesting definition. It takes some time to see that this is the right definition, but it is. And then in a paper with Victor Beresnevich and Lei Yang, we proved that this set is absolute winning. So for every D. So it means that for every D, that there is from this it follows that there is a badly approximable, a real number that is badly approximable by algebraic numbers of every degree. So it's absolute winning in every degree, and then you can take the countable intersection. So this generalizes the classical result, and in another direction, you can think of orbit closures of the times-2 map that avoid the fractal set. So earlier we had here we could do this with countable intersections with the countable sets, but here this is really a generalization of that. So no matter what is K, if you are trying to avoid, if you look on all the orbits that all the real numbers in the unit interval whose times-2 orbit orbit closure avoid that set, then it's dim K counterwinning. So if K is the Hausdorff dimension of K, alpha is the Hausdorff dimension of K, then you can do that. You can get away. You can get away from neighborhoods of points in K by removing just beta to the minus alpha balls where alpha is the dimension of K. So for example, you can take if dim K, if K is countable, then dim K is 0. But you can take, this is not true, so you can take uncountable sets as well, whose Hausdorff dimension is 0, and then you can get away from those type of sets as well. Okay, this is everything I wanted to say. Thank you for being here still.
Thank you, Erez. Actually, you have some time still. You started later and you finished earlier, so if you would like to say something, then it's welcome, more than welcome.
I can show you the proof about the proof that I skipped, but maybe I'll wait for more questions if you have. Thank you.
Okay, thank you again. So questions, remarks or questions?
Can you just remind us what's the Hausdorff dimension of a set?
Well, I don't want to give it a definition, but it quantifies coverings of the set K. So if it quantifies how many balls you need to cover the set K. So, well,
okay.
For example, the dimension of the Cantor set, or the middle third Cantor set, is log 2 over log 3. Okay. Because you just need 2 to the n balls of radius 3 to the minus n in order to cover the Cantor set.
It's normalized by the radius. Okay. So yes. Yeah. Okay.
So it's quantifies the rate at which this number goes, the logarithmic rate at which this number goes.
Okay. Thanks.
Yeah, but there are many open problems about those type of questions, and really, what I tried to convey in this talk is that those two new results are actually mainly mainly come from a better understanding of the game theory that is involved in those constructions, and I mean less so in the number theory and dynamics.
You mean that IDs from game theory helped in these recent results?
So
you mean that IDs from game theory helped the new results in this field?
In a crucial way, yes. I mean, for example, these two results. So this result, especially, the way we prove it is we play we use this characterization that we saw earlier of this characterization of Cantor winning sets as those sets that intersect every large enough set. So, and this was not known in 2011, for example, to the people who, well, even in the case alpha equals 0, it was not known to them that this characterizes the Cantor winning property, or the absolute winning property, and it was mainly revolutionized by many people, but David Simmons was a key player, and I guess he knew some game theory. He knows a lot of things, but he also knew some game theory. So it will not be surprising to me if there is some other games that are involved in that way to be invented in order to be useful for applications that are interesting in number theory and dynamics.
Thank you.
Thank you, Erez. How large is the community about that are working on this type of applications? Can you express it in any way that
any integer?
In any
it should be approximable, yes.
Any non-offensive way. Well, yeah, I'm very happy to see your community and to know about people who are interested in game theory and in infinite games. Yeah, there are quite a few people working in this field. Already those people that I mentioned in the talk are like 10 people, and they have students and you know, McMullen was involved at some point, so this is an interesting topic.
Erez, I already asked many questions. I hope you don't mind one more. If you go back to the definition of the alpha diffuse set,
go back. Alpha diffuse. Yeah, I need to go back. Wait, what am I doing? No.
I think you have to move yes forward. Thanks. Well, my question is, it looks a little bit related to alpha's dimension. Actually,
Yeah.
I might be completely off, but it looks like an upper
No.
bound or a lower bound on the alpha's dimension, something like this.
Yeah, it's completely equivalent. Well, this property is completely has a completely equivalent description if you just use the support of alpha's regular measures. So every alpha diffuse set supports an alpha's regular measure with a dimension bigger than alpha, and I guess the support of every alpha's regular measure with an exponent alpha has a subset that is alpha diffuse, or maybe for every alpha prime that is smaller than alpha, something like this. But in terms of intersection with those supports or diffuse sets, this is equivalent because of this property. Yeah. Thank you.
Thanks.
This is actually what we used. There was some techniques in Diophantine approximation that worked for. There is some trend in Diophantine approximation to replace results about the Lebesgue measure with results about every other measure or some other natural measures, and then there are some techniques that allow you to quantify measures that are measures of neighborhoods of rationals, with measures that are not Lebesgue, not necessarily Lebesgue, and then this is what we used to prove some of the theorems. Okay.
And thank you very much again. I stop